In this video for VCE algorithmic students, we cover proof by contradiction. It's quite a sneaky idea. To prove something is true, we assume that it might not be true, and then we show this logically leads to a contradiction, i.e. something else having to be both true and false. That means our initial assumption, our initial proposition, must be true. It's important when we do this to make sure that every step after our original assumption is logically sound, so that we end up with an untenable result. The only thing then we can fault is our initial assumption, which means that not P must be false, which means P must be true. We'll start with a few mathematical proofs as they are more familiar to you, but we will get into coding and graphical proofs as they are more likely to be examined. Now, the first step that we're going to go through a few examples of is to get that contradictory assumption correct. So suppose I want to prove that prims always produces a minimum spanning tree. Which of these would be a good initial assumption? Would we assume that prims never produces an MST, or that sometimes prims fails to produce an MST? Well, if we were to say that it's wrong that prims never produces an MST, that doesn't prove that it always produces an MST. That would just show that sometimes it might, sometimes it might not. What we need to assume is that sometimes prims fails to produce an MST. If we prove that that assumption is wrong, we're saying it's impossible for prims to fail to produce an MST, which means prims always does in fact produce an MST. Hopefully you can see the difference in logic there. Let's take some more examples. Pause the video as we go along and think about what you would assume, and then work through a proof of what must be false. To prove that root 2 is irrational, we will assume that root 2 is rational. That's quite easy. I mean, there's just one thing or the other thing. There's not really much that can go wrong there. Suppose we want to prove that a tree with n nodes always has exactly n-1 edges. This actually wouldn't always be proved by contradiction. We can prove it more directly just by logic, but we could assume we'd have to make two assumptions. We'd have to assume it has more than n-1 edges or less than n-1 edges. And we'd have to show that both of those lead to contradictions, lead to impossibilities, which means it must have n-1 edges. Every undirected graph has an even number of odd degree edges. So these ones where we're proving that everything is a particular thing, what we are going to assume is that there exists one counterexample. Because if it's impossible for one counterexample to exist, it must mean that our theory holds true for everything. So we would suppose there exists one graph with an odd number of odd degrees vertices. And note, we couldn't just say it's a particular odd number. Like, we couldn't say, well, let's suppose there's one exists with 3 odd degree vertices. That would prove that's impossible, but it wouldn't prove it's impossible to have 5 odd degree vertices. So we have to make sure we get the level of generality just right. So neither of these two. Finally, for this thing, this is quite subtle. You may have seen this before. We're not going to do it in the video, but it's a nice one to look up. We are going to assume that there is a maximum prime number, because if there is no maximum, then there must be infinitely many primes. Hopefully we've got the idea of what we are looking for. Let's get into the first example. You may have seen this from specialist maths. We are going to prove that the square root of 2 is irrational. And as we said, that means we are going to assume that root 2 is rational. And our definition of a rational number means it can be written as a fraction, a over b. A and b are both integers, and it cannot be simplified further. So the GCD, the greatest common divisor of a and b, equals 1. So what we're assuming is that root 2 equals a over b. We square both sides to get 2 equals a squared over b squared, which means a squared equals 2b squared, which means a squared is even. And if a squared is even, we know that a must also be even. You could actually prove that by a little contradiction. You could say, well, suppose a was odd. That means like 2n plus 1 squared is odd, and you can work that through. So if a equals even, that means a can be written as 2m, where m is some other integer. We can substitute that into line 3 on the left-hand side and say 2b squared equals 2m all squared, which means 2b squared equals 4m squared, which means b squared equals 2m squared. That means that b squared is even, which also means that b is even. So what we have is a and b are both even. However, that contradicts our original assumption that they can be written, that root 2 can be written as a fraction where it cannot be simplified further. That means our initial assumption must be wrong and root 2 must be irrational. Now with this proof, you might ask, why do we have to assume that a and b are co-prime? Well, we get to assume this because if a number can be expressed as a fraction using integers, they've got to either be co-prime already, or we can divide by whatever their common factor is to make them co-prime. So there's no feasible situation where both of these things are untrue, where it's impossible to write a fraction in its lowest terms. If we've ended up with a situation that requires that, we've obviously got something wrong. Okay, next one, a bit more of a graphical proof. Prove that every undirected graph has an even number of odd degree vertices. Have a pause, think, what do we assume? We assume there exists an undirected graph with an odd number of odd degree vertices. Now this one you really have to know all your graph theories to make sense of, and I suspect you'd be guided into it a bit in an exam, but hey, you never know. Sometimes they expect you to have a lot of background knowledge. Now, the degree sum here from the even vertices would be even, and it would be odd from the odd degree vertices, which when you add together it gives an odd degree sum. So just to make sense of that, you'd have a bunch of even vertices. You're either going to have an odd number or an even number. In both cases, the total sum of degrees for those even vertices is going to be even. And then for the odd vertices, we're assuming you have an odd number of odd vertices, which multiplies to give you an odd number. And we know that when you add them together, you get an odd number. You can prove this more mathematically, but for algorithmics, we don't need to go into that level of detail. Now we also know that each edge contributes 2 to the sum of the degrees for a graph. It's undirected. Every edge has 2 ends, and each of those ends contributes to the sum of the degrees, which means the sum of the degrees must be even. But we have already said that the sum of the degrees here must be odd, which means it's impossible to have an undirected graph with an odd number of odd degree vertices, which means every undirected graph must have an even number of odd degree vertices. Alrighty, the next one, this is quite tough. It's quite subtle. It used to come up on exams a bit. I think it's too much to expect to knock it out as an entire proof, but if you're familiar with it and if they do ask like bits of it, it might come up. So we're going to prove that prims always produces a MST. And the mark, it's a bit like proof by induction. In any of these questions, you should hope to be able to get the first mark, which is making your assumption. So assume that for some graph G, prims does not produce an MST. So these pictures here are obviously just to help you understand what's going on. Here's a graph G. Let T be the tree that prims produces. So prims has produced T, which is in red. And we're going to assume that T star is another, well, an MST. It must have a lower weight than T, okay, for our initial assumption to be true. Then we're going to consider the edges added in order, and we'll find the first edge, which is in T, but not T star. So working from the left, hopefully you can see the edge, which is in T, but not T star. And it's this edge here. We know that prims always chooses the smallest edge connecting the current tree to the next vertex. So we're considering on the left there is the part of the tree which is the same for T and T star. And then we've got the pink bit over here. And what we've said is that prims has connected the yellow with the pink using E, and that's diverged from T star, which has connected using F, which is that edge you can see. Now we know that prims has chosen the smallest edge, so we know that E must be at least as small as F. Now let's imagine we take T star and we replace F with E to make T star star. Now what does that mean? Either T star star has a lower weight than T star, which means that T star is not an MST, which contradicts our initial assumption, or it's got the same weight, which means, and that was the tree that E produced, which means T star is not less than T up until this point. So either way, the idea that there is a smaller MST than T is contradicted. Hence, there exists no T star less than T. Now, it's really subtle, and I would be going over that a whole bunch of times, and the way I phrased it is probably like subtle incorrectness. And that's why I don't think this comes up in. I've seen it come up maybe twice, like in this explicit form. But hey, it's interesting. It's worth knowing. But yeah, I always have the sense that it's just saying, well, Prim's always chooses the smallest edge, so of course it's the best one. It just does that with a bit more mathematical rigor and flamboyance. Let's look at an exam question, which will hopefully make you feel better about what is coming up. In this case, we're given an algorithm. First off, let's get the contradictory assumption down, which is to assume that equal degree nodes does not return a pair of nodes for, I don't know if I have to write that every single time. For this type of graph, will probably save you some moments and some sanity in the exam. Now, this relies on, it's actually something called the pigeonhole principle, which I cover elsewhere on my channel. It's not something that's explicitly in the algorithmic study design, but this is fairly recent. It has been tested, so it's worth knowing about so you don't have to figure it out as you're going along. So we can see that lines 2 to 6 will return two nodes if they have the same degree. And if we're assuming that the algorithm does not return a pair of nodes, it means that no two nodes have the same degree. All right, well, let's think about, is that possible? We've got V nodes, and each one has a degree from 1 to V minus 1. So there are V minus 1 possible degrees for V nodes. And that means that at least two nodes must share a degree. And if those two nodes shared a degree, then lines 2 to 6 would return them. So we end up with a contradiction. Therefore, the algorithm must always return a pair of nodes. For another question, which I'm not going to go through here, I suggest you look at 2025. There was a nice proof by contradiction towards the end, which required you to have, again, a little bit of background knowledge regarding number theory. Nothing too complicated, but be prepared that these aren't going to jump out at you, and the more of these you see, the better.